Hi, I'm Dr. Laura Harkness-Brennan from the University of Liverpool. I hope you've been enjoying your online nuclear physics masterclasses. I'm going to talk to you about radiation physics in medicine, and hopefully this will complement the talk by Dr. Amina Powell, who works in a hospital. If you're interested in nuclear medicine, also check out our career showcase, where you can hear Lucy McAreevy talk about her role as a medical physicist at the Royal Marsden Hospital. So first off, I'm going to kick off by telling you a little bit about myself and then talk about nuclear medical imaging and focus specifically on single photon emission computed tomography, or SPECT. I'll then move on to radionuclide therapy, and this will all be from the perspective of a research environment rather than a hospital environment. So as you might be able to tell, I'm not from Liverpool. I grew up in Northern Ireland and I went to Coleraine High School where my A-levels were English literature, maths and physics. My degrees were at the University of Liverpool, where I studied for an MPhys physics degree and then a PhD in nuclear physics. I then moved to the northeast of England to work at a company called Cromec, who make radiation detectors, and then after a while moved back into a research position at the University of Liverpool. After some time, that became a permanent academic position, which means that I do both teaching and research. And so first of all, this was as a lecturer, then senior lecturer, and now a university reader. So what does that actually entail? Well, I teach undergraduate and postgraduate students about nuclear physics, medical physics, and also practical skills. I run experiments in radiation laboratories. I use computer simulations and analyse data. And I get to go to lots of international experiments at amazing places such as Japan, Finland, Switzerland, France, Germany, Canada. And I usually do this with other physicists either from Liverpool or from around the world. I present my work at international conferences and I get to write papers about my research for publication in journals for other people to read about. So the focus of today's talk is about nuclear medical imaging. Now, nuclear medical imaging is used to study biological functions, and this complements imaging tools which tell you something about the structure of the body, which is things like X-rays, computed tomography or MRI. Nuclear medical imaging, however, it tells you about how the body is functioning, i.e. how it's behaving. So emission tomography is whenever you administer a radioactive tracer to a patient and then you map where that radioactive tracer has been taken into the body. You map it by detecting the gamma emissions, either directly from SPECT, which uses a gamma ray emitting isotope, or from PET, which uses positrons, which then annihilate in the body and produce back-to-back photons that you can reconstruct the path of. So I'm going to focus on SPECT. SPECT's used for looking at things like how the heart's working, so looking at coronary artery disease and heart muscle damage following a heart attack. It can also be used to identify cancerous cells and can be used in imaging infection and inflammation, measuring the liver and kidney function. It's really good in the regions of the body such as the thorax, abdomen or brain. Technically, however, I just wanted to describe how SPECT works. So SPECT is whenever you inject a patient with a radiopharmaceutical. So this is a radioactive compound which decays by emitting gamma rays. The radiopharmaceutical is accumulating in the organ of interest, and as it's doing so, it's decaying. And gamma rays are then emitted from the organ, and some of them will be detected outside the body by a gamma camera. So what's in a gamma camera? A gamma camera is composed of a collimator, which is usually a sheet of lead or heavy metal like tungsten with holes in it. The collimator is used to determine the radiation direction of the gamma rays, i.e. what direction they come from, and it's placed in front of a radiation detection system which is composed of a scintillation crystal and a photomultiplier tube array. This information is all sent to a computer in order to present a 2D image as shown on the left hand side. Now SPECT is whenever we actually rotate the gamma camera around the patient and take snapshots of what the radiation distribution looks like from lots of different angles. This allows you to build up more of a picture of what the radionuclide distribution looks like in a three-dimensional way. So just a little example on the right hand side here, you see that when you view this sort of orange organ from different directions, it looks different. So you could be looking at along the short axis or the long axis here, and it tells us about the shape of the organ. So the radiation detectors are used are often scintillation detectors, which are used to absorb the gamma rays and then turn that into a photon of light. and they're usually coupled to photomultiplier tubes, and the job of the photomultiplier tube is to convert the light signal into an electrical signal for us to measure. So these are very commonplace detectors. These are some of the detectors in our radiation laboratory that we use for teaching students at the University of Liverpool, and they're very well understood technology. The collimators are a very important part of the gamma camera because they allow us to determine which direction the gamma rays have come from. So how do we do this? Well, unfortunately, because gamma rays have no charge, we can't deflect them into a direction that we want. So we can't deflect them towards our gamma ray imaging system using electric or magnetic fields. Instead, we just have to either scatter or absorb them. That's exactly what the collimator is doing. So as the gamma rays are irradiating the collimator system, if they pass straight through the holes, then they will make it into the detector, the scintillator detector system. If they come at an angle, then they're going to be absorbed by the lead or the tungsten. So what this will give you is a direct projection of the activity distribution onto the detector. In other words, it's just like looking at a shadow image on a wall. Now, collimators are an important part of a gamma camera, however, they're very limiting, and that's because you can have quite large holes, so the diameters could be large, and short hole lengths, and this would allow you to get lots of gamma rays through the collimator into the detector system. This gives you really good sensitivity or efficiency, but it really offers very poor image resolution. So if you want nice quality images, you have to have small hole diameters and long hole lengths, but then you don't use much of the radiation that you've put into the patient. So it's not an ideal compromise, but it's what we have. Other collimators can be chosen to either magnify or even reduce the image to allow you to better visualize the details of small organs, or to allow you to image a large organ or even whole body, only with a small detector in this case. So this is just a couple of examples. So a converging collimator is used to magnify the size of the object onto an image. So this would be used if you were looking at fine details of small organs. And on the right hand side is a diverging collimator. And in this case, it could be used in something like whole body imaging, where we don't want the gamma camera to be the whole size of the patient. It would be much better if we could look at the whole body from quite a small detector system, just for practicalities and also cost reasons. So depending on what the application is, the medical physicist determines which the best collimator is to use. So this just shows you a little video clip of every time we have a gamma ray interacting, we produce something called a gamma ray path or a gamma ray cone. And to determine the radiation distribution, we're looking for localized regions where all of the radiation cones overlap. So in this example, it's up at the top left-hand corner. In other words, this is where the tumor would be located inside the body. So how can we do this? Well, we use something called semiconductor detectors rather than scintillator detectors, and these offer a lot of very nice properties for gamma ray imaging. In particular, they allow you to measure the energy very precisely, much more precisely than you can with a scintillator detector, and this just shows you an example. So in this case, we're measuring gamma rays which are leaving 662 keV of energy inside the detector, so you would want to get one big spike at 662. Now the thin spike you can see here is being recorded by a semiconductor detector. In other words, there's quite small uncertainty in measuring that value, whereas the scintillator detector records quite a wide spread of these values, which is undesirable. So because you have to measure energy quite precisely to be able to reconstruct the cone very accurately to try and find out where the gamma ray came from, we have to use semiconductor detectors in this system. This is what semiconductors look like. So on the left-hand side, we've got a lithium drifted silicon detector, and on the right, just beside it, a planar germanium detector. They allow you to measure both the energy and position of gamma ray interaction, which allows you to track back where they came from. These detectors are housed inside a special house called a cryostat, and this was actually developed by a national science laboratory in Daresbury, which is near Warrington in the northwest of England. And this has been designed to be compatible to work in strong magnetic fields, so that you could actually do the gamma camera imaging at the same time as MRI, which is currently quite difficult because the scintillator detectors with photomultiplier tubes don't work very well in MRI fields, because the electron paths inside the photomultiplier tubes all get bent and deformed. So that's quite an exciting project, and I just wanted to introduce another project that we've got at Liverpool, and that's in radionuclide therapy. So I know that Amina's already discussed a little bit about how radionuclide therapy works, or how we use radionuclides to treat patients, but I just wanted to talk to you about this from a research project point of view. So just a reminder that in radionuclide therapy, the aim is to target a tissue, so something like cancer, via a radioactive compound. And if it's taken up into the body to the tumour and the radionuclide decays within that tumour, because it's decaying and emitting short range particles like alpha particles or beta particles, that means that all of the dose, or a lot of the dose received by the patient, is locally within that tumour. That's really nice because it spares the healthy tissue around those regions. So on the image here, I've just got like little hotspots to show like dose patterns from a radionuclide therapy image, and then on the right hand side, this would be more traditional radiotherapy, where you get beams of radiation passing through the patient to target something in the middle here. So with external beam radiotherapy, this is really the most common type of radiotherapy, but it does have some disadvantages because the beams have to pass through healthy parts of tissue in order to get to the part that you're trying to treat. So radionuclide therapy is a very, very strong and exciting type of treatment for cancer, and also for benign diseases like benign thyroid disease. So in this case, a radiotracer usually is administered to the patient with either a fixed activity level, which is typically in the range of about 3 to 10 gigabecquerels, or it's scaled according to the mass of the patient. What we're really interested in is how much dose the patient receives, because the more dose the patient receives, the more biological damage there'll be. And although that sounds bad, it's actually what we're trying to do. We're trying to cause biological damage to the DNA structures of the tumour, to stop them reproducing and causing more cancer to occur inside the body. So the dose, just wanted to define it here as we might not be totally familiar with it. Dose is just the amount of energy that is absorbed per unit mass of tissue inside the patient. So at Liverpool, what we're doing is designing a special gamma camera that allows you to measure how much dose has been deposited in different parts of the body, and to do this much more accurately than what can currently be done in the hospital. So our aim is to use a gamma camera to measure the activity distribution in the body, and that's because the amount of dose you have in the body, in that tissue that you're interested in, is directly proportional to the activity that's been accumulated inside that region. So the formula here just is D equals A times S. So A is what I'm going to talk about here because this is what we're directly measuring in our project. But just for your interest, S is called an S factor, and these are just tables of information that are recorded in the hospital, which allow these calculations to be performed. So we don't measure S directly in the dosimetry; we only measure A. So how do we go about measuring A or the activity in the tumour? So what we want to do is look at how the activity in the tumour changes over time. So that's what this plot is showing. So it's what the measured activity is as a function of the time post-administration. In other words, at the left-hand side, is it being injected into the patient? And then it goes up to a peak, and it rises at the start because this is it accumulating inside the tumour. So remember, it's not instantly taken up, it needs some time to get there. And then it decays away according to the half-life. Now, if you've started to look at some of the materials for the instability session, you might already have had a go at the exponential decay worksheets. Now, for these worksheets, you'll have had the experience of looking at exponential decay that's applicable to half-life. The half-life that those worksheets are talking about are whenever the radionuclide decays such that the number of nuclei decays by half every half-life. So this is actually called the physical half-life. So that's to do with the radioactive nature of the compound. But in addition, whenever you put the radionuclide into a biologically functioning person, what happens is that the body also processes that compound and tries to get rid of it in other ways. So not just by radioactive decay, but for example by sweat, by breathing it out, anything to do with biological functions of the body. So this formula here just shows you how you calculate the effective half-life, and the effective half-life takes into account both the biological half-life and the physical half-life, and it's really important to use the effective half-life when you're talking about patients, because sometimes the biological half-life plays a much more significant role than the physical half-life, and vice versa. So we're trying to reproduce and understand this decay curve in the gamma using the gamma camera. However, gamma cameras in hospitals are not really designed for this kind of purpose, and that's because in therapy, very high activity radionuclides are used, because remember, what we're trying to do here is to actually damage the cells. So you administer high values of activity, whereas in diagnostic SPECT, which is what the systems are designed for, the activities are actually quite moderate or low, because you're not trying to damage the person, you're just trying to find out what's wrong with them. So because they're not designed for those high activities, the system can become quite overwhelmed by the number of gamma rays that are being irradiated, and it can't cope with the measurements. So this can give you inaccurate activity calculations. It can make it difficult to separate out volume features, which is called volume delineation, and it can give rise to something called dead time, which is this overwhelming loss of count. So you get lots of gamma rays coming in, and the detector system just can't keep up with measuring it, so you lose that information. That's obviously a problem, because then you would underestimate how much activity is inside the patient and how much dose the patient's received. Couple that to the fact that the radionuclides used in diagnostic SPECT are very different to those used in radionuclide therapy. So the gamma ray energies also tend to be quite different. So gamma cameras are designed mostly to work with low energy gamma emitters, so things like technetium-99, which emit gamma rays of 141 keV. However, in radionuclide therapy, quite often the gamma rays have higher energy, and in this case the collimator might not be able to stop those gamma rays, so you get quite a fuzzy looking image, and you get lots of scatter of the gamma rays through the collimator system, and then you get quite poor performance. So at Liverpool, we've been developing a system which is to try and overcome those kinds of problems. So it uses a collimator with semiconductor detectors with a really compact electronics readout. The energy resolution is really nice, much better than scintillator systems. So this allows you to separate whether or not the photons or the gamma rays have scattered on their way into the detector system. And that's because as the gamma rays scatter, every time they do that, they lose a little bit of energy. So by measuring the energy, we can decide whether or not it's been scattered. But in order to do this, you need to be able to accurately or precisely measure energy, and semiconductors are really much better at that than scintillator detectors. The system also has really small detector pixels, and that allows you to have a really sharp image, in other words, really good position resolution, and it also allows us to operate at really high count rates, much higher than what the current diagnostic imaging systems are able to cope with. We've also designed our system to have a special collimator which reduces scatter and also throughput, because remember, there's loads of gamma rays being emitted in this process, and we don't really need to see all of them in order to get a good image. And this allows us to improve our image resolution and also our dead time. In the project, we've worked with hospitals, so the Royal Liverpool University Hospital, the Royal Marsden Hospital, and we've also worked really closely with a UK-based detector company, Chromeg Limited. Just wanted to show you an example image from the system. So in this case, this is called a medical phantom. So medical phantoms are used to assess the quality of an imaging system. So they are usually, say, structures or pieces of plastic which you can fill with say cavities that you fill with radiation. So in this case, that's exactly what we've got. We've got a thyroid phantom. So a thyroid is a butterfly shaped gland in the neck, and in this case the little black regions are cold rods. In other words, in these regions there's no radionuclide present. So the green region is where the radioactive solution is, so we don't expect to see any gamma rays come from these points because there isn't any radionuclide solution there. However, when we image it in a clinical system, so a diagnostic system, we can't tell at all that there's black spots here. It just looks like there's radiation everywhere all through it, and you get this kind of strange pattern forming. The strange pattern forming is because the gamma rays are so high energy, they're able to pass through the collimator, so you can almost see the shadow of the collimator shapes. So all these little holes are the holes of the collimators that are not working very well for this type of radionuclide. At the top, we have an example image from our own system, and you can see the little dark regions that we want to be able to see, so that's great news. And you see, probably should have mentioned, this region here is quite a hot spot. It is noticed on the clinical system as well as the Depict system, and that's because the region here indicated by the circle has got twice as much radioactivity in it, so we expect to see lots more radiation, which is why we get this kind of hotter region in the image. So the Depict image is better than the clinical image, which is really great news. So there's lots and lots of exciting future challenges in nuclear medicine. So things like improving diagnostic image quality, improving quantification in imaging, reducing the dose to the patient, developing new types of radio tracers, things that I haven't even had the chance to talk about, like imaging during proton beam radiotherapy. So we've got lots of new and exciting proton beam centres coming online in the UK. 3D real-time imaging during surgery, and also big data is becoming a really big field at the minute in medical imaging. So I hope that some of these really exciting unanswered questions are going to be answered by you in the future. I'd just like to thank you for listening and hope that you enjoy the rest of the Nuclear Physics Masterclass. Thank you. So at Liverpool, we've got a research project which actually aims to remove the collimator system from the gamma camera to allow you to use more of the radiation that you put into the patient to actually, so those gamma rays make it into the image itself. So in other words, it's a high sensitivity or high efficiency version of a gamma camera without compromising on the image quality that you normally get with having a collimator based system. How do we do this? Well, like I said, we take the collimator away and we replace it with a radiation detector. So we've got at least 2 detectors in the system as shown in the picture on the slide. And then we use a principle called gamma ray tracking. So in nuclear physics, we've got a really good understanding of how gamma rays interact inside materials. And so we can use the physics principles by measuring the energies and the positions at which the gamma rays interact inside the detector, we can track back how they've scattered through the system and find out where it came from. Now, by doing this, we can actually use 100 times more of the dose that's put into the patient, or more of the activity that's put into the patient. So this would allow you to reduce the amount of radiation you have to administer to the patient, or it might allow you to image much, much more quickly, depending on what the hospital want to do. We can also do something called multiple isotope imaging. This is when you inject 2 different types of radiopharmaceutical or radiotracer into the patient and image the distributions together at the same time. So this could allow you to look at, for example, metabolism by looking at how glucose is taken up into the body, whilst also looking at how blood flows through the body. So these tell you different things in terms of the way that the body's functioning, but doing it at the same time is a lot better for the patient and for the hospital.